you see my screen?
Recording is on.
Yes.
Yeah, because I have two screens. I'm sharing it on the big one, so it's better.
Yes.
Can you see my screen? Okay.
Yes, I can see. Yes.
Okay. Thanks. So let's begin. Yeah. So hello everyone. I'm Tianzu, as Masood just introduced. I'm very happy to get this opportunity to share my not so successful exploration on high-speed packet processing. I have known Masood for it's already 14 years. Yeah, we were classmates together. I mean, and then we all began to take the career as researchers.
Yeah.
Masood has always been a researcher that I admire and look up to. I mean, he always attacks the most difficult problems with tenacity, determination, and combined with his technical skills. So when he mentioned me about this event, I was pretty excited. So yeah, let me continue. So the work I present today was originally developed in the context of network function virtualization. Where I think you guys are all familiar with the concept. In NFV, network services are built from software network functions running on commodity servers. So, but today for this talk for AI audience, I would like to frame the work in a broader way. The core question this work tackles is, can we use data-driven methods to understand the communication system performance without instrumenting the communication path itself? So the question actually is becoming increasingly important because the communication infrastructure is no longer just fixed routers and switches. It now includes software packet processing, virtualized network functions, programmable devices, containers, virtual machines, smart NICs, recently GPU communication stacks, and eventually AI-assisted control if we go for autonomous networks in the future, which we are. And the challenge is these systems are highly flexible, but the dark side of this advantage is their performance is also hard to reason about because they run on the shared infrastructure, and many performance problems are caused not by the network control logic or the network function themselves, but by the complicated interactions between the network functions and the underlying computing infrastructure. So today's stories, I would like to sell a simple but what I believe powerful idea is a high-level network performance leave low-level hardware fingerprint or footprint inside the infrastructure, and can we use I mean, if we can read those footprints or fingerprints carefully, we may infer the high-level KPIs like throughput, latency, and possible potentially performance impairments without touching the fast critical packet path. So yeah. So let me start with the motivation. I would like to present the idea in a more clear way. On the left side, we have NFV. It's quite a promising networking paradigm. Instead of deploying dedicated hardware equipment, appliance, or people call middle boxes, we can implement network functions in software, and then we chain them together. And this gives network operators flexibility because they can compose, upgrade, scale, and deploy network services in a much agile way. And in principle, this is very attractive. Yeah, because we can run heterogeneous network functions like firewalls, load balancers, network address translation, intrusion detection, deep packet inspection, and others, on general purpose servers. But the right side shows a less rosy picture. It's the reality, because once these functions run on the commodity shared infrastructure, they will compete for resources like the CPU share, like the cache, the memory bandwidth, the NIC, namely the network card queues and the PCI buses, also the NUMA socket related quick passes between the NUMA sockets. This creates a fundamental tension because the logical network service may look clean and sane and deterministic, but the physical execution environment is noisy and shared. So a network function may face slowdown, not because its code changed or there is some bug in its code, but because another workload stole resources from it, like CPU cycles, or pollute the underlying cache, or saturate the memory bandwidth, or alter the packet processing path, for example, at the network card. So for communication systems, it's dangerous because performance impairments do not only reduce the throughput, they may create more severe problems like jitter, like latency spikes, packet losses, and eventually like service level agreement violations. So the key message I would like to deliver is, even although software rights the network infrastructure can bring agility, the shared commodity infrastructure brings contention. So if we want a reliable communications systems, especially in this current AI, large language model era, we need a performance intelligence that understands both facets. And then, so if the performance is unpredictable, right, the natural response is let us just measure the performance directly inside the packet path. And yeah, it's true, but this can create what I call the diagnostic paradox, because in high-speed packet processing, measurement is not free. If we insert a packet level or flow level telemetry, like flow classification, or maybe customize the timestamping or packet mirroring into the data path, the monitoring system itself consumes resources and becomes part of the problem. For example, here on this slide on the left, we have a lightweight network function, namely the layer 2 forwarding that mostly forwards packets, doesn't do so much. It can operate efficiently at line rate because the packet path is simple. But on the right side, if we augment it with more functions like with more like heavy in-band monitoring mechanisms, we make the processing logic heavy. So the system now, for example, on the right side, the system now has to classify the flows, timestamp the packets in a specific way, collect a specific packet level or flow level statistics, and or may even maintain some additional states, depending on the specifics of the network function we are talking about. Here is only a simple example. So these operations may be useful for diagnosis, but they can also disturb the system that we are trying to observe. So I put two result plots here, show this so-called observer effect. When feature collection is placed inside the critical data path, the throughput can drop and the latency can rise as the service chain become longer. Here is just here are just some of the numbers I got from my local infrastructure, but the exact numbers depend on the workload and the system configuration. But the principle applies to any system in general. In high-speed network, in high-speed software packet processing, intrusive measurement can become part of the performance problem. And so this motivates the central design question of this work, namely, can we monitor performance without modifying or burdening the fast packet path? So And this is where the work makes its main conceptual contribution. Instead of collecting packet-level statistics inside the packet bus, we collect the low-level hardware features out of band. The original implementation used the Linux perf, to capture the PMU, namely the performance monitoring unit events. But I think, the broader idea is not limited to PMU. The broader idea is to observe the execution, the underlying execution environment, including the hardware counters, the cache behavior, the instruction activities of the CPU cores, the memory access patterns, and other low-level hardware signals that can provide us some insights or information. And this method has, in my opinion, three advantages. First, the approach is non-intrusive. It doesn't insert any heavy feature collection into the packet processing path. Second, it's black box compatible. Namely, it doesn't require the source code or the implementation internals of the virtual network functions or detailed prior knowledge of the input traffic or the network system in general. And the third, it can still work when packet payloads are encrypted or protected, because we are not inspecting the packet content here. We are only observing how the system executes. So this is I believe a core distinction with the other works. We are not trying to understand what the packets contain. We are trying to understand how the infrastructure behaves while processing those packets. So the key idea here is we move from packet or flow level monitoring to the hardware infrastructure level performance inference. And so one natural question at this point would be, can the hardware features can really review network performance? The answer is that software packet processing interacts deeply with the commodity server architecture. So a packet doesn't just pass through an abstract network function. It touches the network card, the DMA passes, the CPU cores, the private layer 1, layer 2 caches of the CPU, also the shared last level caches if the functions are deployed on the same NUMA socket, the memory buses, and sometimes even the cross NUMA interconnects. So here, the slide, we show the three major sources of resource contention. The first is the CPU share interference, because network functions, especially those from Intel DPDK or PF ring zero copy, they run at they run at the busy polling way, which means they need stable CPU cycles to support their operations. If co-located workloads or scheduling effects disturb those cycles, packet processing performance can degrade a lot. And the second source of contention is the cache, especially the last level cache, including the DDIO, which is short for direct data I/O. It's a part of the cache reserved by Intel CPU architectures. Also, the network card traffic and the packet burst may interact with the last level caches. This can, evict the useful network working sets of some network functions and increase their cache misses. And the third one is the memory bandwidth saturation. Once the cache behavior degrades, packet I/O and the network function state access may hit the main memory more frequently and creating additional pressure to the memory bus. So the important point is that these bottlenecks or contention sources of contention, they are not purely network layer phenomena. They are cross-layer performance phenomena, arise from the interaction between the communication workload and the underlying hardware execution environment. So this is why low-level hardware features can carry information about the high-level KPIs like throughput and latency. Later, when there will be a slide showing the correlation between those low-level features and the high-level KPIs. And then I would like, because we use in the end we use machine learning for performance analysis. But before going that way, I would like to briefly mention a field exploration I had with the so-called causal discovery or causal methods, because at this point, we know that if the hardware features are informative, can we discover something directly from it? Many of my teammates at BioLabs, they have the research background, the causal research background, which has been around for decades. And they would like to know if we can apply those methods to our case, to this NFV system case, to expose the root cause of performance degradation and the performance bottlenecks. This was actually a reasonable direction to explore, because causal discovery algorithms, they look very attractive. They seem to offer structure and explanation, not only like a prediction like the machine learning approaches. But in this setting, they they didn't work very well, because they have two strict assumptions that will never apply in real network systems. The first issue is they must, and they assume causal sufficiency. And this algorithm usually assumes that all the relevant confounders, I mean everything, including the confounders, can be observed. But the hardware telemetry is full of hidden factors like kernel activity, interrupt behavior, scheduler decisions, background processes, the queues at the network card, the traffic burstiness, and unobserved workload interactions. It's impossible to observe everything. And the second issue is the cyclicity, because causal those causal algorithms, they mandate that we must, the interactions between the hardware features should not contain any cycle. But in reality, hardware and system behavior are usually full of feedback loops. For example, CPU scheduling can affect the cache behavior. The cache behavior can affect the execution time. Execution time can affect the queuing, and then the queuing affects the future resource usage. So a cyclic graph assumption doesn't usually apply in our case. And the third issue is that the signals are high dimensional, correlated with different scales, and sometimes not IID distributed. So many counters are strongly dependent on each other, and finite samples can make the graph discovery unstable. So in the end, the classical causal discovery is not the right tool for this problem. It took me 1 year to finally realize this and give up. And the machine learning is better suited for the immediate goal, namely the infer performance from noisy correlated high-dimensional hardware features. And it allows us to optimize directly for throughput and the latency prediction, even when clean causal structure is usually unavailable to us. And here is the architecture we propose. It has 3 phases. The first phase is the data path. network functions will process the packets normally, and the key requirement here is that the packet forwarding should remain uninterrupted and undisturbed. We don't want the diagnosis logic, all the packet, all the traffic, all the system monitoring mechanism to become part of the problem. And the phase 2 is telemetry. The system will collect hardware features out of band. In the original work, this is mainly done through PMU events via the Linux perf or Intel PCM. But conceptually, this telemetry layer can be extended to other hardware level data sources. And the phase 3 is performance and analysis. A data-driven model here will map the collected features to KPIs such as throughput and latency. The principle is decoupling. Packet processing and performance inferences are separated. The data paths remain focused on forwarding the packets or steering the packets, while the telemetry and the inference pipeline observe the system from the side. So this is why we call it a non-invasive or non-intrusive. It doesn't need to modify the NFV, the network function code. It doesn't need to inspect the packet payload. It doesn't need to insert heavy telemetry mechanisms into the fast data path. So instead it asks what can the underlying execution environment tell us about the performance of the communication services. Here, I would like to briefly, and before looking at the result, I would like to briefly explain the experimental setup. This is an old setup. Currently, we are upgrading our hardware, but it's a general configuration and observations still apply. So here I only show the original version. The testbed uses a single commodity server with 2 NUMA nodes for fast prototyping. The basic design is to isolate the traffic generation and measurement from the system under test. So for example, on NUMA node 1, we use a traffic generator named Moongen for traffic. It generates traffic patterns and measures the end-to-end KPIs. On NUMA node 0, we deploy the system under test, namely the target network function service chains. And the two sides are connected through fiber links between the NIC ports. This allows the testbed to emulate a high-speed packet path while still keeping traffic generation and network function execution separated across the 2 NUMA nodes. And the software stack we use is DPDK. And we specifically use the FastClick and OpenNet VM, two of the most prevalent open source NFV frameworks, but we are currently extending it to include more NFV frameworks in the ecosystem. The tested cores are isolated from the kernel scheduler with hyper-threading and turbo boost disabled to reduce unrelated noise. The experiments include line rate tests, iMix style, mixed packet sizes, and load stimulus and resource stimulus, which I will introduce in a later slide. Throughput and end-to-end latency are measured at the receiving end, while hardware features are collected out of band on the SUT side. The setup allows us to evaluate the core claim, namely can we infer packet processing performance from hardware telemetry while leaving the packet path uninterrupted. Here we examine whether the hardware features actually carry useful information. This slide shows the correlations between selected hardware features and the final throughput across a network service chain with 5 network functions, namely the bridge, payload, scan, NF, router, DPI, and firewall. The first observation here is there is no single feature that dominates everywhere. It means we should not expect a single rule, such as if this counter is high, the throughput is low, something like that, because the performance depends on multiple interacting hardware features. The second observation is that cache-related features are consistently strong, especially the last level cache features. They usually show strong, very high correlation with throughput across network service chains. This is also coherent with the observations of many prior studies. And this makes sense because high-speed packet processing is very sensitive to cache behavior. If packet metadata, network function state, and the packet buffer interact poorly with across the cache hierarchy, usually on our servers we have 3-level caches. The throughput can degrade quickly. And the third observation is the network function specific behavior. For example, the DPI has an unusually high correlation with memory stores. This matches the intuition because deep packet inspection requires more memory related activities than simple forwarding network functions. The hardware features are if we can derive anything from this slide, there are 2 points I would like to express. The first is the hardware features are predictable, are predictive, not predictable, predictive, and the relationship is multivariate. So this motivates a data-driven model rather than a single handcrafted threshold-based approach. Then I would like to describe a little bit about how we generate the data, because we need to train the machine learning model. We define 2 kinds of stimuli. The first is the load stimulus. This changes the external traffic pressure at the network card. The traffic can be configured using different packet sizes, rates, including the IMIX traffic. This helps us observe how the system behaves as input demand increases. The second is resource stimulus. This introduces co-located stress processes that compete for CPU, cache, and memory resources. This models for example, the so-called noisy neighbor effect in the shared infrastructure, which is a well-studied topic by prior studies. These 2 stimulus are complementary because the load stimulus asks the question of what happens when the communication workload itself becomes heavier. And the resource stimulus asks what happens when the infrastructure available to the workload becomes worse. So in real deployment, both problem will happen. The traffic changes over time and the infrastructure contention changes over time. So a robust performance inference system should be exposed to both types of variance. So this experimental design, I think, is also useful for the COM4AI style research, because it treats the communication performance as a cross-layer phenomenon, not just a network layer metric. Here is this slide is trivial. It's about training a machine learning model to predict the obtained feature vector. So I will just mention it briefly, because currently we are going for auto ML. And namely, we do not want to rely on a specific model. We are open to any data-driven models. Here because this is the original design, it's a multi-layer perceptron. The input is a vector of hardware features, and these features have different scales. So pre-processing and the regularization matter. The output is the predicted KPI, throughput or latency. And the reason we decided to use this 3 or 4 layer MLP is that the relationship between the hardware features and the network performance is non-linear. The cache contention, the memory pressure, the instruction behavior of the CPU, and the traffic load do not combine in a simple additive way. So the MLP is not presented as the only possible model. It's just a practical nonlinear model that works well in this specific setting. Future versions of our work could use gradient boosting, temporal models, may even graph neural networks or hybrid ML and system models. The broader message is once we decouple telemetry from the packet path, we need an inference engine that can convert the low-level hardware signals into the network-level performance intelligence. So what can we do with this, for example, this simple MLP? First, let's look at the throughput prediction. The left plot shows a regular input rate pattern. The throughput rises and falls in a structured way, and the prediction closely follows a real throughput curve. The right plot is more challenging. It shows a random rate pattern with volatile changes. Again, the model tracks the real throughput reasonably well. And I think the important result here is not the curves look very similar. The important result is that the model can recover high-level throughput behavior from low-level hardware features. It can indeed do so. It doesn't inspect the packet payload. It doesn't need the internals of the the network function design. It doesn't insert heavy monitoring into the fast packet path. So this supports the core idea of our work. Network KPIs leave measurable traces in the underlying hardware environment. So this is like the bridge between systems and AI. The AI model is not looking at the packet content. It's learning from the execution footprint of the communication system. Then here we have we compare the proposed approach with the prior performance prediction methods. The comparison contains 3 dimensions in general. The first is the feature set or the signal source. Because earlier methods used more limited measurement. For example, some works only one of the work only use the cache access rate. The other work combines the last level cache features with the memory bandwidth features. Our work actually uses a broader set of low-level hardware features. And the second is the model. Prior work include linear regression models and gradient boosting. This work uses an artificial neural network to capture the nonlinear relationships among the hardware features. The third is the topology scope, because those 2 prior methods, they mainly focus on a single network function. Our work evaluate more complex service chains and DAG, directed acyclic graph style service topologies. The result shows that in our evaluated scenarios, the proposed approach improves the prediction accuracy and reduces the average prediction error compared to the prior art. But I would like to phrase the conclusion of this slide more carefully, because this doesn't mean the artificial neural network model we use is universally better in every deployment. It means richer low-level telemetry feature set plus the nonlinear modeling can improve the performance inference, especially when the service topology becomes more complex. And then here is one slide I usually don't want to present, but my colleagues would insist because they are like from the machine learning background, and they are really proud of any achievement related to generalizability. But I personally disagree, but I still would like to briefly present this slide. So one possible concern is that the method works only for simple linear service chains. But in this slide, we address this concern by showing that by showing the DAG-style service topologies, including branching and merging, so that they are more complex than a single linear chain. The bottom plots show that the model can still track aggregated throughput trains for the tested DAG-style services. And also in our setting, I remember it's done by a postdoc. She trained she trained the model on the linear case and then tried to apply it to one of the DAG case, and it was very accurate. This is why people, not people, I mean, many of my colleagues would like to claim robustness and generalizability. I personally disagree because the data I generated for different topologies have very similar behaviors at the feature level. So I don't expect it to generalize well to any service topologies with different network functions. Yeah. Okay. And then I would like to show the latency prediction because throughput prediction is useful, but latency is usually more critical for communication systems. So this slide we show the latency prediction in three scenarios: a linear topology, a DAG style topology, and a resource stimulus scenario, which we artificially create contentions. The latency is generally harder to predict than the throughput because it's more sensitive to queuing, to scheduling delays, to traffic burstness, to the tail effects. So we shouldn't expect a perfect curve matching everywhere like in the throughput case. But the result shows that the model can capture major latency dynamics, especially periods where latency rises sharply. And so this is operationally valuable. Even if the model is not perfect at predicting every point, it can provide early awareness that the system is entering a degraded latency regime. For operators, this can trigger deeper diagnosis or migration. So for future autonomous networks, it can become an input signal for safe control loops. Then I would a little bit of strategic thoughts. So the first, I think I would like to discuss the operational value of this work, even if it's still ongoing and many works still need to be done. The first value is the non-intrusive integration, because the approach doesn't require modifying the network function code or inserting heavy telemetry mechanisms into the fast packet path. It can be seamlessly integrated alongside any existing NFV frameworks or software packet processing frameworks. The second value is the early service level violation awareness, because the system because the system itself doesn't guarantee the service level agreement by itself, but it can provide a useful warning signal when the low-level hardware feature behavior suggests that throughput or latency might degrade. The third value is NFV agnosticism, because the approach doesn't require deep knowledge of the network functions internals. This matters when the services are heterogeneous, third-party, or closed source. So this is especially relevant as communication systems become more software-defined and more AI-managed. We need models that can reason about system behavior without requiring intrusive instrumentation everywhere. And then, yeah, sorry, I would like to skip the last slide. And then, here is the future direction, because the original work focuses mainly on the PMU-based hardware features. But in future systems, PMU should only be one of many data sources. This slide shows a broader direction, including we can integrate, for example, the C group signals to capture the resource accounting and pressure. We can use the kernel and the scheduler signals to observe the soft IRQ behavior, run queue delay, and the context switches. We can use the counters from the network card to capture the queues, the drops, or the imbalances on the receive side scaling. And we can also use, for example, even if I'm not very experienced, the eBPF and the runtime signals for performance tracking, to track the DPDK or XDP behavior. So this broader telemetry, which we are trying to work on, yeah, it has two advantages. First, it can make the deployment more realistic, because currently many experts are still criticizing this work as a toy case. And some environment may not even expose the PMU counters, but they can expose the C group kernel network card or eBPF level signals. Second, it improves the diagnosis, because the different telemetry sources point to different bottleneck classes. And then the last slide. So finally, let me close with a broader research horizon. The current work is like a single. Yeah, there are several ways to extend this work. The current work is like a single node NFV performance prediction study, but the idea can be scaled in several directions. First, the network-wide performance reasoning is the immediate way for us to go, because instead of reasoning about one service, one or a few service chains on a single node, we can reason about many nodes, many servers, and many interacting resource domains. Second, it's about continuous data and model pipeline, because the performance models need to be adapted as drifts happen. For example, the drifts in workloads, in the kernel upgrades, in the network card, in the traffic patterns, or the evolvement of the deployment configuration. Third, we should include broad ecosystem support, like what I just mentioned in the previous slide. We can integrate more hardware sources, or possibly the AI cluster communication signals to enhance the quality of prediction. So The AI systems increasingly depend on complex communication infrastructure, and the infrastructure is too dynamic to manage purely by static rules. I think this is where the current approach we propose to connect to a larger vision. It gives us a path towards AI-assisted performance diagnose and eventually safer autonomous network control, if it can happen anytime in the future. So let me conclude with the 3 takeaways for this talk. The first is high-speed software networks are flexible, but their performance is vulnerable to the shared resource contention. The second is in-band monitoring can distort the packet path, so non-invasive telemetry is essential. And third, the low-level hardware and hardware signals can be used by ML models to infer high-level performance, including throughput and latency. The broader message is that the communication systems can become more observable without becoming more intrusive. So that's all. Thank you very much. I'm happy to take questions.
Thank you very much, Zhang. It was very interesting talk. It was very interesting, and yeah, actually, so it was a new direction. I see. Okay, so we can connect basically the low level hardware system to like the throughput and latency of the network in the system in the higher level. So let's see if there is any question. Is there any question here?
Hi, Tore here.
Yeah.
Yeah, I just wondered about the instrumentational setup. You had like one node with two
NUMA nodes.
Yeah, two NUMA nodes, and
yeah.
So, don't you think like the QPI or UPI would interfere between the NUMA nodes? Did you isolate it or?
Currently, I would avoid deploying the network functions of the same service function chain to across different NUMA nodes, because when I do that, the performance will degrade a lot, maybe more than 50%. So usually I would like to avoid it. But the cross NUMA, the QPI the limited QPI bandwidth. I mean, this point you mentioned, it can be used for interesting case study when misconfiguration happens. For example, the network operators deploy the network functions by mistake across the different NUMA nodes, and then our method can be used to detect this misconfiguration. That's only one use case. Yeah.
Yeah, and I was wondering about the inference. How is it run? Is it CPU only inference or?
Currently, it's because here I only showed the perf features. Yes, it's mostly CPU features, but then I integrated the Intel PCM, which will contain some more advanced features aside of the CPU, including like the memory at the memory level, at the PCIe level. Yeah, and in the future, I would like to include more, because currently I don't think these features provide us a holistic view of what's really happening inside the infrastructure.
Okay, I don't know if the recording ends now, but on your slide, more hardware feature sources to integrate. You didn't have a slide number on the slide, but there was
sorry.
One of the last ones. So
yeah, here is like I listed here as like a future direction. It's not a purely future, because I'm currently trying to explore it.
Yeah, definitely when I advocate for. I worked in Silicon Graphics and Cray before, and PCP Performance Copilot is very good at having very little invasive on monitoring. So PCP can do, you can have many plugins without it being very invasive. And it's used by Amazon and a lot of other companies. So I could suggest that, and also like Masoud and I and a student had S-Flow plugin to
S-Flow plugin. Okay,
yeah,
let me take notes.
to PCP, and which we would need to improve upon to make it productive or production worthy. But I think it would be a good thing to add. I mean, it was running on the monitoring was running on a DPU, Bluefield 2.
Bluefield, yeah.
So, but I think it could be a good thing to get into, because I don't think any S-Flow, there are no other S-Flow based plugins for this PCP. So
yeah, actually, speaking of DPU, I have one question for you and Masoud. Maybe, are you using? Do you have experience with the NVIDIA DGX?
Tor has, I guess. Yes.
Yeah,
right?
we have.
How do you compare it to the DPU? I mean, in terms of performance, because we purchased the two DGX. And that doesn't seem to be very good. It cost us like 10,000 euros.
So maybe then, if it's okay, maybe I can stop recording if there's no any other questions for this. Then we can, because then I can. Is there any other questions regarding the talk?
Yeah. Sorry for digress.
No. I mean, this is cool, but I think that this part I can exclude it from the recording. If there is
please.
any question, no. Okay, so maybe I have one, and then quickly I see that actually, Ron, I have a question regarding the data set size. How big should be this data set size to have like a good accuracy?
Let me think. I don't remember the exact number because I collected a lot. It's usually currently we, for example, when you work with perf and PCM, usually it can collect every 100 millisecond, and then this is the frequency, and I keep it running for like one night, maybe not one night, one day. So it's 24 hours. We can just estimate the number of data points.
So then this is like
it's like it's about 2 weeks, I think, in the end.
Okay, then this is quite large.
Yeah, it's like a big data set with I don't remember 100 gigabytes or something. Yeah.
Okay, great.
100 or 50. Yeah, I don't remember the exact number.
Exactly. So thank you very much. And if there is any other question regarding the talk, if not, I can stop recording. And then we can. Yes.